Right, okay, we're going to have a look at enzymes and catalysts. Now, what's the difference? Well, an enzyme is a catalyst, a biological catalyst. And what's a catalyst? Something that speeds up the rate of a reaction without itself being used up. Let's have a look. Right, so we're looking at catalysts and enzymes. We're going to have a look today at a catalyst and an enzyme. We're going to have a look at an experiment involving hydrogen peroxide, H2O2, a rather peculiar and dangerous substance. And what we're going to do with this is we're going to add a catalyst, and we're going to use one called manganese dioxide. And this will make water plus oxygen. Now, hydrogen peroxide isn't a very nice stuff, and we meet this sometimes in the body. And so the body produces an enzyme called catalase, and that turns hydrogen peroxide into water plus oxygen. Now, quite often when we do this experiment, we use liver. But with the COVID-19 going on at the moment, getting hold of liver seems to be a bit more hit and miss. So we're going to use a different system. We're going to use potato. It doesn't work as well because in something like an animal, they want to try and get rid of the hydrogen peroxide really quickly. In a potato, the need for getting rid of it quite so quick isn't quite as desperate. So here, the enzyme, there's less of it, and it doesn't work generally quite as fast. But we'll have a look at both and see what happens. So what are we going to do? Well, let's have a look at what this experiment is all about. We've got a conical flask, not one of my better ones. The conical flask, we're going to connect this to a piece of glass tubing. And this glass tubing, I'm going to put in a bowl of water. In the bowl of water, I'm going to put over this a special item called a beehive shelf. And then over that, I'm going to place a measuring cylinder. I'm going to fill this all up with water. With our hydrogen peroxide in here, we're going to add some catalyst, and our reaction will start. We put the bung in immediately, gas is produced, and we will collect the gas over water. And this is a classic chemistry experiment for doing catalysts. We're then going to repeat the experiment, but this time, instead of using the catalyst of manganese dioxide, what we're going to do is we're going to use the catalyst of potato. The enzyme catalase. I'm going to see if we can get the same reaction. Now, I certainly can't guarantee it's going to work, but we'll certainly have a go and give it a whirl and see what happens. Right, let's go over and have a look at the experiment. Now, the experiment is nearly set up, but not quite. I've got one little bit missing. Typical tradition in my household when I want to get something out. It all gets jammed up. Right, I'm now ready to have a go. Okay. Now, what have we got here then? I've already put some hydrogen peroxide into this little conical flask. I've got my potato, my knife all ready to have a go. Cutting it up. I've got my catalyst, which is manganese dioxide. Spatula ready to go. And now we're nearly set up over here, but not quite. And we've got to try and solve the rest of the problems here. I'm going to collect the water, the oxygen that we're going to produce in this measuring cylinder, 100 ml measuring cylinder, and we've got a piece of tubing that's going to go into here, down into this beehive shelf, and here I can see it's got a little gap where the glass tubing can go, and a hole which is going to let the gas out. And it resembles a beehive, hence its name. So my piece of glass tubing, I'll show you, goes along and runs along here, and that bit goes into the glass, over the glass tubing, such that we can see the glass tubing there, and on top of that we've got this measuring cylinder. So we want to fill this up with water. So let's do that. I've learned over the years that you can put cold water in here, but it actually works an awful lot better to put warm water in, because then it doesn't freeze my fingers when I stick them in there. I need to put enough water in to cover the beehive shelf and a little bit more. So there's the beehive shelf covered, and I want to put a little bit more in, basically just enough so that I can put this measuring cylinder in quite comfortably. And we seem to have that set up with enough water in there. Now, what I've got to do is fill this up with water. Then, what I've got to try and do is I've got to quickly tip it upside down, not letting any air in, and then put it in place. And this is usually a challenge for many students. Fill this up. I want to get rid of any air bubbles. I really want to make sure that's reasonably full. And then we have all sorts of excitement. Some of them think that they can put their hand over it like that, and they can get it in there like that. And I managed to get two tiny air bubbles in there. It doesn't matter. So I can position then this in place over the hole. Not necessarily the best way of trying to do this. There's a much easier way of trying to do this. And that uses a bit of cling film. So what I'm just going to do is I'm going to tear myself off a piece of cling film. I don't know anything like that much, but I might want to do this again. So I've got myself a piece of cling film. Let's fill this up with water so that the rim. I'm trying to make sure I don't have too many bubbles there. And now, really quite easily, I can put the cling film over the top. There's my cling film holding the water in. I can then easily place it upside down, remove the cling film, and there we are, not an air bubble in sight. I'm just going to loosely clamp that so it doesn't fall over. My cling film's not very good when it's wet. Alright, so we've got that nearly set up. We've got this flask. We've got the tubing. And I want to position the tubing so that it goes into this beehive shelf. With a little bit of wiggle. I can do that. I'm going to move this so I can look down. And I can check that the glass tubing is right in the centre of this hole. And I've got this against this side, so I can make sure that it's always going to be in the right position. And we're now ready to go. I've put in 50 centimetre cube of this hydrogen peroxide. So this is 30% hydrogen peroxide. It goes off quite quickly, so I can't use it for more than a month or two old. So let's get out some manganese dioxide. This is not particularly nice stuff, and being a catalyst, we can be quite careful with this and recover it. So I'm going to take a little bit of catalyst, and we're going to have a look. Now, we can measure this accurately to see the time it's going to take for how much oxygen to be produced. And I can get a stopwatch out, and I can record the time, and I can record the amount. I'm not going to do that this time. We're going to do more of an anecdotal system just to see how well it works. So let's take some hydrogen peroxide, manganese dioxide, put it in, and off we go. And I've got my oxygen, quite a lot, and there is my hydrogen peroxide going beautifully. I put the bung out because the amount of gas coming out comes very quickly. And if we do this experiment and put some washing up liquid in there, we can do nice experiments like elephant toothpaste. So that experiment is already over. It was quite quick. That is quite hot. And you can see that the reason I didn't bother to get out a stopwatch was by the time I think I pressed go, it would be done. So I didn't bother. Now we're going to try the same thing. And I'm going to reset the experiment up. And this time I'm going to use some potato. So let's set it up. And we're about ready. Okay, so my tube is set up. We're all ready, apart from the fact that now what we've got to do is get my enzyme prepared. So that's all ready. I'm just going to take this off because it's in the way. I did get a minor bubble, but I don't think I'm going to worry about that. Let's have a quick mop up before we start. Okay, we're ready to go. I want here a piece of potato, and what we're going to do is we're going to chop up a small amount of potato. So I'm only going to want a small bit. And what I need to do with this is cut it up into small bits. If you watch the last experiment where I was playing around with foodstuffs, you know that I do this extremely badly. So I'm trying to chop it up fairly finely using my best culinary skills. And I'm trying to basically damage as many cells as I can so that they will release the enzyme. And I've given myself a fair bit in there because I've done this before and it doesn't work terribly well. Okay, we've got our clean conical flask, and I'm going to put in a little bit of hydrogen peroxide. We're then going to connect it back up. Set this in the right place. Right, we're ready to go. So let's put the enzyme in and see what's going to happen. I'm going to give it a bit of a shake to mix up, and what we should see is now it's starting to work, and you can see it is not as fast. It's working, but it's not as fast as the catalyst. And this doesn't give a good idea of how fast enzymes really work. It is working, but there's not much of this enzyme in there, and so it doesn't work terribly quickly. We're getting, with the same strength hydrogen peroxide, you can see it's working much slower, but it is working. The reaction doesn't work unless we've got an enzyme present or we've got a catalyst present. But it is working, and it's working steadily at a fairly steady rate, breaking down the hydrogen peroxide into oxygen. Now, when I do this with liver, this is as exciting as using the manganese dioxide. In fact, sometimes more so. Many of the times I've done this with students, they don't manage to get the lid on before the reaction is actually over. Whereas this one, as you can see, is performing at a fairly steady rate. And we're getting one bubble about every 3 or 4 seconds. And every 3 seconds there. We're getting a constant stream of hydrogen peroxide being broken down into water and oxygen. Now, there is one advantage to this system. If I feel the temperature of this, it's not feeling hot at all. This one, on the other hand, it is still really too hot to hold, and we got it virtually boiling. If you tried that in your body, that wouldn't be terribly exciting, just producing a little bit of enzyme, and what we'd find is you're dead. Okay, so I'm going to leave this experiment cooking. It's not doing any harm here. And what we're going to do is going to have a look at another experiment using an enzyme. And maybe this one's going to be a little bit quicker. Right. Okay. Now, for this experiment, what I'm going to do is we're going to do an experiment with amylase. And to help with this, what I'm going to do is we're going to look at it twice. I've got here a small amount of starch, which I can put into a test tube, and I've already got some enzyme. This is amylase. Now, amylase is quite a useful enzyme. It's found in the mouth. And what we're going to do is I'm going to take some iodine solution and I'm going to put 1 or 2 drops of iodine in each of these wells. Now what we're going to do is we're going to do an experiment with starch, and with this starch what I'm going to do is we're going to react it with the enzyme amylase, and we're going to see what happens. There's my tile set up. What we're going to do is I'm going to take some enzyme and this enzyme, which is bacterial amylase, I'm going to put with some of this starch solution that I made up earlier. So I'm going to take some this starch solution. That is not a clean test tube. And there is my starch solution, and I'm going to put that in there. Now I'm going to repeat this experiment, so I'm going to take another dollop of this starch, just making sure it was a nice clean test tube. Not the best thing to fill it up in. And I've got about the same amount of starch in there. It'll do. It's That's near enough. And what I'm going to do is I'm going to add a small amount of the enzyme to this. Now we will repeat this experiment a couple of times, and the second time that I'm going to repeat it, I'm going to use some of my spit and see how we go on from there. Right, we've got our tile, we've got our enzyme, and we've got our starch, and we've got a stopwatch. And what I'm going to do is I'm going to take a pipette and every few seconds we're going to take a drop of starch out. So there's my pipette ready to go. That one we're not going to do. Paul's just giving me the stopwatch so we can see. And what I'm going to do every 5 seconds is I'm going to take a dollop out and I'm going to put 1 drop in there and squirt this back in. And we can see at 0 time, I haven't added any enzyme. We've got here the blue-black colour of starch. And what I'm hoping to see is as I go along, this may change. And hopefully my starch is going to be turned into something exciting, which is not starch, a sugar that we saw in the last lesson. Now we'll get another top out. So I'm going to take some enzyme, we're going to squirt it in and start. Ready, go. I'm doing as best I can for 5 seconds. Now, I often find that when I use bacterial starch, bacterial amylase, this doesn't work very well, and I'm unimpressed. And it's not got there. And I'm going to stop, because that's certainly not doing what I want it to do. Instead, what I'm going to do is I'm going to put a different source of the enzyme with this one. So let's move that one out the way, and Paul has set me up another one. And we should be ready to go and have a look at this. So I want to repeat this. This time we'll just get 2 more pipettes out. Use that one for the sample. and this one for the enzyme. Right, are we ready? 3, 2, 1, go. Five seconds. 10 seconds. 15 seconds. 25 seconds. 30 seconds. 35 seconds. 40. Ooh. That's 50. Paul's got another one ready for me. I can let just the stuff in this tube go. And we'll stop there. Well, that was much more successful. Wasn't quite every 5 seconds. I didn't want to wait 10, however, because we can see what's actually happening here. So the starch is being reacted with, and we can see that it's gradually getting less and less and less. And in 2 minutes here, the equivalent of a slice of bread has been reduced to sugar. Now, when I watch most of you eat even faster than that. I watched a sandwich being piled into the mouth and it being swallowed sort of possibly without any chewing and just sort of stuffing it down into the stomach. But if you had been an elegant young lady of Victorian times, you've been taught to chew each mouthful probably at least 100 times. And the reason that you would have done that is you had probably a waist of about 16, 18 inches. So you didn't have much of a stomach anyway. And it would actually slow down the process of eating. And if you've tried putting a piece of bread in your mouth and chewing it, and so we've got this idea of enzymes and catalysts. The enzyme is a biological catalyst. And if we look at the other experiment just to see how it's going along, Paul's just going to point the camera at that. We'll see that I think it's actually just about stopped. Let's have a quick look. You ready? And yeah, it's just about stopped there. Potato's not really wonderful at trying to get it going. And Paul can show you there, there's the potato, not really doing an awful lot. I can give it a little shake. We didn't release an awful lot of enzyme. There wasn't an awful lot there to start with, but it has managed to get us about, was that about 30 mils of oxygen? Yeah, about 30 mils of oxygen there. So it works better with amylase, and that experiment we better just have a quick review of. So we took a test tube of starch, and I put a strong solution of starch in there, probably the best part equivalent of a piece of bread in there, probably, and I put in some amylase. I put it in from two sources. There is bacterial amylase, which is quite frankly not as good as the fresh stuff, and that was supplied by some spit, and trying to get the spit going, I find usually it's a good idea to chew a sweet, and that helps produce some of the enzyme. Does have one little side effect. I picked up a raspberry one, so I had slightly red coloured amylase. I apologise for that, but that's where it came from. That was me cheating. What I can do sometimes, and I didn't fancy doing it because I was trying to talk at the same time, is I use a little bit of lemon. Now that's really good. That certainly does produce loads of amylase, but I can't talk very well, so I decided not to do that one this time. Right, so we put some spit in there, and what we found was on the spotting tile. Paul's going to point at the spotting tile for me. This is the advantage of having a good assistant on the camera and also a qualified chemist. So this is our spotting tile. It wasn't quite every 5 seconds. It started off well, but it got worse. So we managed 5, 10, 15, probably nearer 25, 30, 35, probably nearer 45, 50, 55. We didn't record them. 65. 70, let's say about 80 seconds. Let's assume it was about that. And if we look at that, we can see that by this one, we can start to see things really working, and the black colour disappearing. And the black colour is just disappearing as we go down through. So we can see this took in the region of about 55 seconds to work. The enzyme worked really quickly anyway. That was actually getting rid of all of the starch, not just most of it. So we're looking at a time to get rid of the starch. It does really work quite quickly. Why does this enzyme work so quickly? Well, I've already explained. You put the sandwich in your mouth, it's gone, and you haven't even really had time to get the enzyme to work on it. So if you can put the food in your mouth and chew for a few moments before you actually swallow, then there's time for that enzyme to work and start breaking down that carbohydrate into its simple sugars. How does it work? Well, it works really a little bit like this. We have what we call the lock and the key model. So let's imagine my enzyme has a funny shape in it like this. This is my lock. And along comes this molecule. Now, this molecule fits more or less exactly into this particular enzyme. So let's see what happens. Let's try and show that they are different for you. And this fits in there. Now, when it fits in there, something happens to this enzyme. And what happens is it changes shape very, very slightly. And in this case, it's going to put a lot of strain on this joint between two particular molecules. And what's going to happen? It's going to break. No longer required. The two molecules fall out. And I've just managed to break down my one molecule into two molecules. So this is the lock and key model to try and explain how enzymes work. And now that enzyme can be released to bind again. And we can keep using this enzyme over and over again, breaking down this molecule into its constituent parts. Enzymes do one of three jobs. One, they break down large molecules into smaller ones. An example of this is the one we've just had a look at. This is amylase. It works as an enzyme on starch, which is sometimes called amylose. And it breaks that down into a sugar called maltose. So we're breaking down large molecules into smaller ones. A lot of this is the process of digestion. Once I've got my molecule in one format or another, then I might want to change a molecule. If you look at digestion in more detail, one of the things that we do is we make a sugar called glucose, and we change that glucose into another sugar, fructose. They are very similar to one another. They're just isomers. And there's a new enzyme called isomerase. And isomerase does that. Now, if you were to buy glucose, it's relatively cheap. If you want to buy fructose, it's relatively expensive. It's fruit sugar. If you've got some enzyme isomerase, then you can take glucose and add this enzyme and make fructose. And this is done industrially to change cheap glucose into expensive fructose. It's also used in your body. Another way we can do this might be we can join molecules together. So we can take small molecules and we can turn them into large ones. And there are many processes in the body that do this. But you don't need to know any enzymes that do this. So we've got this idea of trying to have three functions of an enzyme. Finally, let's just look at the rate of an enzyme. And we often find an enzyme starts off quite quick, but then gradually slows down. And this is here the rate of an enzyme. But it slows down simply here because we run out of the stuff to work on, and that's called the substrate. And our rate of reaction slows down. So there's a couple of experiments to then have a look at. We've had a look at hydrogen peroxide and it working with a catalyst, manganese dioxide. We've looked at it with an enzyme, catalase in potato, but much better if we could have done with liver. Sorry, COVID-19's making shopping difficult. And we've looked at the rate of reaction using amylase on starch. Bacterial amylase, I found, doesn't normally work terribly well, and it does work, but it just takes much longer. It should be the same enzyme, but I haven't been happy with that. Or just use some spit, and that is fresh enzyme. Believe me, I'd only just made it, and it's then used immediately to break down starch at really a rate of knots. There we are. Enzymes, to give you some idea. Now, what we can also do with enzymes, we can look at how they work at what pH and at what temperature. We'll have a quick look at that next time. Take care. I'll see you then. Bye-bye.